if you've seen some of the previous webinars, you'll see a presentation on gas holder demolition in general. This is a MAN gas holder. That's MAN stands for something in German that I'm not even going to try and pronounce. But if you're interested, there's quite a lot of information on the internet about them. And this is a project, Jackson Street is in St Helens, that we completed with Coleman and Company back in, it was 2012-ish, so it's a long time back. But when you start punting around to see a project that make a good presentation, you suddenly remember all the challenges and everything that came with this project. And hopefully you'll understand why I've chosen to share this one with you and see the complexity that was involved. Oh, the client has disappeared there. So the client was National Grid, Coleman and Company, or the Coleman Group were doing the demolition, and we were working as the temporary works engineers for Coleman's for the project. Now, MAN gas holders are low pressure gas storage. They used to be seen in a lot of places across the country. The only place you'll find them now is within steelworks and those sort of industrial areas. All of the ones in city centres have now gone. We took the last one down with Coleman's a couple of years back now in Southall. So they're now all gone pretty much in this country. There's quite a lot left in Europe, but anyway, they're pretty much gone. Now, the way they work is you have a big fixed volume tank. Inside it, you have a piston here, which is this. I want to turn on my pointer so you can see. So there is the piston. The gas, low pressure gas, comes in underneath it, and that's what causes the piston to rise. You then shut off the inlet valve, and the weight of the piston with the chemicals that's on it is what provides the pressure, the low pressure that feeds the gas mains in the area. So quite a simple system, but quite big structures. This one, I think the one at St Helens was probably 80 metres high, 50, 60 metre diameter, something that sort of size. So they're big old lumps. You could see them quite clearly on the skyline in many cities. Now, when we typically demolish these, what we do is we put a series of special cranes we've designed up on the roof here. We then blow the piston, which is the green there, up. So there it is in the down position. We put two big air blowers on the side and we blow the piston up to the roof, cut the roof free, and that forms a big floating working platform, as you can see there. So that's literally floating on a bed of air at about so maximum 2.5 kilograms per square metre air pressure, what we're running at. We then sequentially demolish the structure, working the way down to ground level until we can do it with a high reach. Now, that relies on the sealing system being intact. As you will see, we couldn't use that. So this is a man holder on fire. The smoke pouring out the top there. It wasn't full of gas at the time. There was the oil-filled seal at the base of the piston caught fire, and the whole tank went up in flames, as you can see in this little video here on YouTube. So this did quite a lot of damage to the tank. You can see the heat has actually damaged the shell plates, deformed the shell plates. Inside the holder itself, this is the seal that used to form the seal here between the plates and the piston. So this is what stopped the air leaking past. Now, the fire completely destroyed all the rubber seals and all the oil that sat in it that sealed the holder up. So if you're looking at a section through, this is the shell plate, and this is where the seal was here, and all the bottom of it's full of oil, and this seal was full of oil. And that's what went up. Now, not only did this heat completely destroy the seal on the piston, it also significantly distorted the tank. So the tank was actually 3D scanned. And if you're looking, say, at column 21 here, you can see it's 155 millimeters out of plumb from where it should be. So that's quite significant. Okay, it's not significant in that height, but it's significant when you're trying to make something that seals against the side of a tank. And you can see quite a lot of them around this side here had moved during the fire. So the heat had often clearly got up enough to allow the steel to move to some extent. It didn't fail, but it had moved. So this poses a bit of a problem. We can't demolish it the way we normally do by using the piston. And we know from previous analysis that if you just cut the roof off them and lower it down, these holders will not stand up in the wind. You'll get local and quite large movement of the holder and sort of uncontrolled failures. And given the location of these holders in city centres, it's not really the sort of place to be taking a chance on movement and failure or partial failure of a structure. So dropping the holder, dropping the roof, and then cutting the plate up wasn't really a viable solution either. The roof itself is supported on the 22 columns and is a series of trusses which span back to this ring in the centre here. And this is a big heavy circular truss in the middle here that the roof spans back to. And this will become important very shortly. So you'll see the options. So the traditional options are out. Any sort of method of dropping the roof is out, and then cutting it over the high reach is all out as a solution. So we had to come up with an option to drop the roof in a controlled, engineered manner whilst taking the holder down. Now, I was an engineer on this project, but I wasn't the brains behind it. This was my father. This was Neil, who developed the methodology in conjunction with Coleman's for this. And so this was early on in my career at Andun, so I was just an engineer churning out calcs and drawings for it, but the concepts were not mine. So he came up with 3 different options. First of which here is a screw jack, but a short stroke screw jack. So you would lower the roof sort of 100, 200 mil at a time, then reset, then drop, then reset, then drop, then reset, which would have been quite slow. Next option was a long stroke screw jack, so that could drop it sort of 3.5 meters at a time. And the final option was using manual hoists or manual winches to lower the roof. This was felt to be too slow. This was quite a pricey option when you started pricing up the screw jacks and the cost and all the gimbal system we had designed at the top here to allow it to move freely and not put bending into the screw. So the solution that was settled upon was using manual hoists. Now, even that might seem like a simple option, but it really was not a simple thing to design. So the first problem you come upon is at the top of these holders, the roof is the top. So the column that comes up the edge stops at roof level. So first thing you would do is come up with a way of supporting a hoist above roof level so you can support the roof and therefore lower it. So the first solution was this, which was a steel beam with some RHS sections that slip over the existing columns that allow you to extend the column up by 2.5 meters, 1.8 meters up. That allowed you then to install these brackets we designed to suspend the hoist to then pick up the roof trusses themselves. So that problem was solved. Now, and there it is in the flesh. So that's where the column stops on the existing roof. That's the extension column piece. And then you start seeing these different fabrications we designed. So these here were the column bracket. So these bolt on and use friction to grip onto the column sections. We then have a variety of these different pieces here that drop in to suit. So the principle is that you could support this roof on 11 of the 22 trusses and it would hang quite happily. If you're leaving it long term, you hang it on the 22, but when you're lowering it, you lower on 11, you then tie off on the other 11, and then away you go. This will become apparent, but that's why there's a couple of different drop-in brackets here. And there you can see the hoist in place, and you can see the bracket that goes around the top chord of the truss that forms the roof itself. So there would be 11 of these when we lower it, and they were 20-ton hoists, a couple of 30-ton hoists, which were used next to the crane that had on the roof. So if you think back to that analysis model I showed you, what we found from analysing these structures is that if you need to have some sort of tie within the structure, i.e. just having the roof hanging there wouldn't be enough. You needed to strap the columns back to the roof itself to maintain stability. So we came up with this system here, which you can see there, which is a couple of brackets welded to the roof and then these big straps that go back to a bracket we designed that tied the column. So when we lowered it and locked it off, you installed these lateral restraints here which tie the structure back to the piston, or sorry, back to the roof, which provides stability to the structure. You can also see here the intermediate hangers. So if you can imagine the 22 columns going around in the diameter, each alternate one would be like this, and then the one next to it, and the alternate ones from that would be hoists. So alternate ones are hoists, and the alternate ones from those are these hangers, these hanger details. So we could lower it with a hoist until these go tight. You can then drop the hoist and repeat the process. Now, around the top chord of the truss, we had to have these hanging points. So this is the point at which the hoist attaches to. Again, similar detail to the bracket that clamps onto the columns. We've got these heavy steel fabrications that clamp on underneath the top chord of the truss. And as an added backup, we also had these, what we call safety chains. So around these here, we put chains down around and under the truss and back up to this hanging point just in case something went wrong. Safety really was a priority throughout all these works, and there was an awful lot of engineering challenges to overcome. So this goes through a bit more detail of the tyre system. So it's got a bracket that as you pull tighter, it grips harder, and it pulls the columns back tight up to the end truss and provides stability to the structure. And there's the drawing, and there's reality. I think they did a pretty good job of making the drawings match reality. Now, you'll note a lot of these systems rely on clamping and friction, which was quite a big hazard. So there's an awful lot of testing that went on beforehand to demonstrate that the system that went on the top chord of the truss worked, and that the system that clamped onto the column worked. And everyone, in fact, was tested in situ. So we pulled them back to back, and you put a jack in place to prove that there was sufficient friction there to stop it sliding. So this wasn't just done on numbers, this was done with numbers and then validated with physical testing to demonstrate that we could do what we were planning on doing. The sequencing of this job was incredibly tricky, from cutting the roof free to how we then control the lowering and the locking off operations. There was an awful lot of work gone into working out, communicating to the client as to how they had to do these things, and indeed working with them to work out what was feasible and what wasn't feasible. That snapshot's not going to mean a great deal to you, but it gives an idea of the sort of drawings that were put together to explain how the system and how the project was to be installed. Now, I came across this in one of their method statements when I was going back through preparing this for this presentation, and it's probably the best explanation there is of how you lower the roof. So we've got 22 columns around the outside, and you've got the so if it's hanging on the red ones, okay, the yellow ones represent the hoist. So we can release the hoist because it's hanging on all the alternate red ones. We can then move the lower hoist bracket down. We can then move the hoist down. We can then reattach the hoist and raise the roof slightly. Then we can detach the upper, we can then detach these ones because there's now slack in these. We can then move these brackets down, and then we can lower down, or we can lock off. And then you can cut down the shell plate, and then you keep repeating. So that's the basic principle of how the works were done. You then raise it again to get the slack, and then you lower to the next level and just repeat. So it was quite a time-consuming, tricky sequence to communicate. And there it is in reality. There's the guys who are sitting up on the roof using the hoist to lower the roof. That's fairly early on. I would suggest we've literally just finished the first cuts there. We're about to start lowering it for the first time. So at that point it's hanging. So there's one column to hang from. There's an intermediate one with nothing hanging, and there you can see the next hoist just around the corner there. You imagine you've got this structure which is sort of 60 meters across, and you've got 11 men on hoist that you've got to try and coordinate and make sure they're all lowering at the same time. Not a particularly easy operation for the site team to manage at all. And you can see there it wasn't particularly quick either. The distance they were dropping in an hour wasn't huge. So it's quite a slow, methodical, controlled methodology. And that's a good picture there. You can see the hoist, you can see the intermediate bracket, the hoist, the intermediate bracket. And this is the crane rail you can see here that the cranes operate on, which are then used to cut the panels out and lower them to ground level, which I'll come on to in a bit. Now, to actually see the process of lowering it, this is literally how this roof was lowered. 11 20-ton hoists, or near enough, all being lowered at the same time. And they had to do that from 90 metres or 80 odd metres down to 50 metres in height. So it was quite a slow, controlled methodology. So that was just the challenges for raising the roof, for lowering the roof. You've then got the normal challenges associated with these gas holders, which is taking them apart and using a craneage system to do it. So these are cranes that we designed specifically for the job for Commons, and the crane rail system that spans from column to column. All of this was sitting on the roof while we were raising and lowering as well, to add a little bit more weight to the system, make it that a bit more challenging. And the panels are literally sliced up into 3 panels deep systems, and then lowered down the side of the structure to ground level and taken away as scrap. Once we'd got down to 50 metres, which is the point at which we'd decided the holder we'd analysed and assessed that the holder would remain stable without the roof, they then had to take a lot of the weight out of the roof. As you can see, they're cutting out shell plates and members that weren't required to reduce the weight of the structure, and then getting a dirty big crane to lower the roof to the floor. So you can see there, a lot of the weight's been taken out of the structure, and we're slinging from the central ring and then lowering away from there. So you can see it's a big old crane with the counterweights that are there. I can't remember what size crane it was, and I couldn't find it quickly when I was putting this together, but it's a big crane. And there it is at the bottom. So you can see they left one lot of shell plate in as access to allow the slinging and the rest of it. And there it is being, at ground level, there it is being lowered. And there it is pretty much sliced up and ready to go. And you can see you've got the 50 metre high holder walls around you. And then the high reach machines brought in, and then just tear it down effectively, as you can see there. And I think there's a little video here. There is indeed a little video that someone's taken from outside the site. And you'll just see the machine ripping it in. Get to a bit, you can see the machine. There you go. Yeah, you can see the machine there, just grabbing the sheets, shearing it and pulling it in. Given the guy sitting 50 metres down, he's doing pretty well to work that accurately, as far as I can tell. Not sure I could do that. There it goes, and just gets dropped to the ground level, because the high reach has a standoff, so he can have his arm out like this and the cab's back over here. So it's quite safe to drop the steel like that. There's 4 or 5 minutes of that, but I'm not sure any of us want to watch 5 minutes of that. I certainly don't. Now, perhaps the scariest thing about this entire project is excuse me, it's the fact that we put all of this effort into the engineering, making sure we had everything correct, had sufficient factors of safety in places, were with inside safe working loads, etc., etc. Only to come back one day and find that a number of the hoists had failed, which immediately set alarm bells ringing throughout Coleman's and throughout Andun to figure out what had gone wrong and why it happened. You can see there one of the failed links. You can also see there some of the damage to the links on the chain hoist here. And what it turned out to be was the manufacturer had got the instructions wrong, which they issued. Now, all of these hoists were bought brand new by Coleman specifically for this job. And unfortunately, the instructions that came with it were wrong. They have what we call what we call the draw-up height, which is the distance between the top block and the bottom block. These hoists have been chosen specifically because we could get the top block very close to the bottom block, which made a lot of things simpler, as you've seen in the presentation. Now, what it did also do was it meant that these chains were getting pulled around the pulleys inside, and they were getting nicked. And these little nicks were forming stress raisers, which made the chain susceptible to failure. Thankfully, the whole system be designed that if you left it overnight or you left it for the weekend, it was locked off, and it was hanging not just on the hoist but on the intermediate brackets as well. So there was no real danger of the roof failing, but it was still still quite a large shock to all of us that these brand new hoists could fail in such a dangerous way. So it's always acts as a bit of a reminder that no matter how much effort you put into a job, the planning and the engineering of it, there's always something that can come out of the blue that you least expect and can catch you out big time. And that was that on this project. You can see here the damage that was done inside the hoists themselves. They took all the hoists away, reconditioned them, sorted them out, and they came back again, but still far from ideal. I think in one of the presentations I found, Coleman suggested this was one of their biggest challenges, and I can well agree with that. It was, even from my perspective back then, it was a very challenging project and a lot of technical issues to overcome and solve to get the job done properly. So a bit